guys, welcome to section 3.1. Before we start 3.1, I wanted to do one more example from section 2.8. So this is kind of like, section 2.8 continued. Let's get a little smaller here. Okay, so section, what did I say? 2.8. And the last thing we did was the higher derivatives. So I want to explore the graphs of higher derivatives. Okay, so let's say we'll graph f here, and we'll graph f prime here. And now let's do our higher derivatives. Let's do f double prime and f triple prime, or the third derivative. Okay, so let's do this. Let's have our original function do something like that. Okay. So again, remember how if we wanted to graph then the derivative of that function, first we would find the zero, right? And when I say find the zero of the derivative, we'd have to figure out where the tangent line has a slope of 0. And then at that point, that would be our 0 on f prime. And then we would see where our function has a negative slope for the tangent. So that's where our graph is decreasing. So that means we're going to be down here for our derivative. So our slope is negative. Again, that means that our derivative is negative. So we'll be below the x-axis. And then finally, when our original function is increasing, that means our tangent line is increasing as well. So we have a positive slope, and so that means the derivative is positive. So after this 0, it's going to be positive. And it turns out, as we are, creating our tangent lines, the slope is decreasing and increasing at the same rate. So it's going to look something like this. Okay, so there you go. Okay, so that was kind of a review, and now what we're going to do is we're going to find the graph of the second derivative, and how we do that is really how we just drew the first derivative, but to get to the second derivative, we go from our first derivative. So we have a straight line, so the tangent line to a straight line is really just the line itself. So when we're talking about the rate of change, in this case, when we're talking about the rate of change, how fast this line is changing, well, isn't that just the slope? So in this case, when it's a straight line, the slope of that straight line is your double derivative. Okay, so let's look at this. We have an increasing line. So is the slope positive or negative? Slope's going to be positive, so we don't really know exactly what it is, but maybe we would draw it right here. We would just want it to be positive. Okay, so that's horizontal line is y equals m. All right, and then finally we have the third derivative. So to do the third derivative, the graph of the third derivative, we would want to look at the second derivative to determine the rate of change of the third derivative. So let's look at this horizontal line. And what's the rate of change of the horizontal line? What's the slope of the horizontal line? The slope is 0. Right? So the slope of this line is 0. So that means over yonder, that's going to be our third derivative. It's going to be at the 0. Okay. So there you have it. So if we know how to draw the graph of a first derivative, we can draw the graph in a similar way for the second and the third derivative. All right. So now let's officially begin section 3.1. All right, and then this is called derivatives of polynomials and exponential functions. Okay, so the first one we're going to start with, so remember what we just did in section 2.8. To find the derivative, we have to find the limit as h approaches 0, yada, 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 right? And it's really difficult. But what we're going to do in this section is we're going to figure out all our wonderful shortcuts. So our life is about to get a lot easier. So we're going to start off with the most basic function. It'll be a linear function. And let's give it a slope of 0. So that would be like a horizontal line of some sort. Okay, so let's say it crosses the axis at C. So this is the equation f of x equals c. And what's the slope of a horizontal line? It's 0. So if f of x equals c and the slope is 0 of that linear function, that means the derivative has to be 0, right? So we can prove this next part graphically. We can say that the derivative, I'm going to use that Leibniz notation, the derivative of a constant c is equal to what? 0. All right, so that's like our first theorem. And we can see that visually. Let's see how we would prove it using our derivative definition. All right, so here's what the proof would look like. So let's start, let me get a smaller pen stroke. Let's start with, we're taking the derivative of a constant c. And according to 2.7, 2.8, that's the same as the limit of f of x plus h minus f of x divided by h. Okay, so if we were to plug in our input into our function c, well, it doesn't matter what the input is, right? If it's a constant, whatever we put in, we're always going to get back c. So we're looking at 0 divided by h. And if 0 is in the denominator, we're looking at 0. So this is going to be 0. All right, remember limits, we don't care about h equals 0. It's what happens around h equals 0. And if 0 is in the numerator, then the answer is going to be 0. All right, so we were able to prove that the derivative of a constant is 0 using our definition from chapter 2 and by also looking at the graph as well. Okay, so that's our first theorem to make our life easier. Let's look at another theorem. We are going to next want to find the derivative of x. Oh, that's I didn't like that. Let's try that again. Oh, no better. Okay, so f of x equals x or y equals x. That's the one that goes right down the middle. Okay, so let's talk about the rate of change of this line. And again, let's just do a little side note about the rate of change. Rate of change of a line like this. And we saw this in our last example too. Rate of change of a line is the slope of the line. That's really what the slope is. It's a rate of change, how fast the y's are changing as a ratio to how fast the x's are changing. So the rate of change of a line, whoopsies, is the slope stop it. Give me 1 second. Oh my goodness. Okay, sorry about that, is the slope of the line. So rate of change of the line is the slope of the line. And since we know that the rate of change is the derivative, then we know that, oh my goodness, that the rate of change, or the slope, is the derivative. Okay, so let's look at this line, y equals x. What's the slope of the line? M is equal to 1. So that means if we were to take the derivative of x, it has to be equal to the slope. And so it's equal to 1. All right. And there you go. Remember, the slope is 1 for a couple reasons. Like if y equals x, if we were going to do change of y over change of x, it's 1 to 1, right? Because y equals x. Also, you know, y equals x, if we write it in y equals mx plus b form, the coefficient on the x is 1. So we also know, that's how we also know the slope is 1. Okay, so with that, we know that, or we have our new theorem, which is that the derivative of x is equal to 1. Okay, so now what we're going to do, well, so we know two derivatives. We know the derivative of a constant is 0, the derivative of x is 1, and now where we're going with this, we're going to want to find out, and what we're going to explore is, what about f of x equals x to the n? What's that derivative? Okay, so that's where we're going next. That's what we're going to figure out. Okay, so to do that, let's go to section 2.8. So we're going back to chapter 2, and we're going to look at something. We're going to look at the derivative using the old school method. Old school as in one section ago. Okay, so section 2.8, I'm going to turn in my textbook. Hopefully you have your textbook open. Ooh. And we are on page, goodness gracious, 162. And we're going to let f of x equals x squared. And we're going to find the derivative. So we're not doing the whole thing. We're just doing the derivative part. Okay, so we're going to go old school. So if we want to find this derivative, we have our limit definition. All right, and we're going to plug in x plus h first, and then we're going to subtract just x squared, then we're going to divide it by h. Okay, so we know the deal. We've done this enough before. We're going to square out the top, right? X squared plus 2hx plus h squared. And the x squares will cancel, and we're going to be left with 2xh plus h squared divided by h, okay? Now there's an h in every term, so we can cancel out that h. We have 1, 2, 3 terms, so we're going to want to cancel it 3 times. All right, and then as h approaches 0, now we can just plug it in directly since 2x plus h is continuous at h equals 0. And so the derivative is 2x. Okay. Let's examine something else. We're looking for patterns here, right? Because remember that first question, what about f of x equals x to the n? What's that derivative? All right, so let me remind you guys, this was another question from your section 2.8 homework, number 20. This time we wanted to find the derivative of x cubed. So if we wanted to find that derivative, we'd plug it into our formula for derivative. Vampire sneeze. Prevent the spread of germs, excuse me. And if you simplify everything in this expression, we did an example of like this in class. Simplify, cancel that h, plug in h equals 0, we're going to get 3x squared. Okay, so let's summarize what we have so far. So from number 19, we had that the derivative of x squared was 2x. From example 20, we have that the derivative of x cubed equals 3x squared. And then, similar way, I'm going to tell you what the derivative of x to the fourth is. And let me see if you guys can figure out the pattern. It's going to be 4x cubed. You guys pick up on the the pattern? So let me show you what's going on. So the exponent, when we take the derivative of a power function, right, like x to the n, we bring down the exponent and then we subtract 1 for the new derivative. So let's do it for x to the fifth. So if we wanted to take the derivative of x to the fifth, we bring down the exponent in front and then we subtract 1 from the exponent. So the derivative is 5x to the fourth. Do you want to guess what the derivative of x to the sixth is? 6x to the fifth. In general, and this is called the power rule, this is true for any real number n. The power rule says that the derivative, here I'll write power rule. And this is true for any real number n. So real numbers, fractions, decimals, negative numbers, the whole shebang. X to the n, if we were going to take the derivative of that, we're looking at n x to the n minus 1. So again, we bring down the exponent and then subtract 1 from the new exponent. Okay, and then like I was saying, it doesn't have to just be a positive integer. It can be a fraction. N can be a fraction. So let's say we're looking at x to the 5/4. If we wanted to take the derivative of that, it's the same process. The derivative means that we bring down the exponent and then subtract 1 from the exponent. All right, you need a common denominator. 1 is like 4/4. So we're looking at x to the 1/4. Okay, and it also works with negative exponents. So for instance, x to the -3. If we wanted to take the derivative of that, we're going to bring down the exponent with the negative sign, and then we're going to subtract 1 from the new exponent, for the new exponent. And be careful, because -3 minus 1 is going to be -4. All right. So let's take a pause here, and then we'll continue in part 2.